Sorry, I start recording now. Okay, it's plus integral and q es y, pero I know que y es x squared. Es x squared. Multiplication dy, pero dy is 2x. dx. And this go from -1 to positive. Okay, this is easy. It's integral from -1 to +1 of the x squared plus 2x cubed, you multiplication like that, minus 2x dx. Well, this is piece okay. The answer is 2 terms. This is another possibility. No parameterization, always using t. You know parameterization, using maybe x and maybe x. No y, never y. Okay, do you understand very well circulation? O sea, es line integral, vector line integral, circulation. And remember, the circulation is the interpretation of the circulation. So you consider that the integral function, que es a vector field, is a word. However, we have another of the vector line integral, que es a flux integral. Let me try to explain flux integral. Entonces the students say, bueno, professor, I never understand flux integral. But it's the same. It's the same. What is the idea? Flux is the technical word que measure how much vector field passes through C per unit of time. Suppose we have a curve like that, and we have a vector field like that. And the flux is the amount of, suppose que the vector field, in this case, the best interpretation for the flux is not force, sino es velocity. Velocity of fluid, of water maybe. Entonces I need to compute how much liter of water passing through this surface. Entonces, how you compare that? Bueno, it's complicated because the vector field is a variable, and the geometry location for the curve is also variable. Entonces, you compute using this integral, que es integral in the curve C of the vector field that, pero no tangent vector, sino normal vector. I don't know why this. O sea, compare. Circulation is something like that. This is circulation. And flux integral is using normal vector. Entonces, bueno, I suppose que normal vector is something like that. Normal vector. Tangent vector, sorry. Is something like that. And normal vector is something like that. Well, actually, we have two normal vectors. Out or in. Normally, you assume it's out. Okay, this is a convention. Because I need to find how much passing through C. Entonces now, let me try to do the sketch to understand this. What is the relationship between normal vector and tangent vector? So tangent vector we define like tangent vector, sorry, ds. Tangent vector, ds, que es dr vector, ¿no? Y es dx, dy. I need to find the expression for the normal vector, ds. Okay, this is the thinking. I don't know why, in this part, every book every lecture using letter M and no capital M. Remember when we study the Frenet-Serret formulas, well, we study capital N, like unit vector. But no, in this case, everyone call letter M, but it's the same thing. Okay. Okay. Suppose we have one trajectory like that. And I pick one point. In this point, and the direction is a specification. It's like that. Now, in this case, we have the tangent vector. In this case, it's a normal vector K1, and it's a K. Wow. And it's a K. This is obviously a K. Unit vector. Remember, this problem is 2D. I promise that after we study flux in 3D, pero now it's flux in 2D. Entonces now I have the K vector, pero K vector is perpendicular in this case to the whiteboard, no? I try to do my best here in 3D to understand the idea. So I can see that unit vector M is equal, let me see, this is the cross product, no? Tangent vector, cross product, K vector. I use the hand right rule. You put the finger pointing first to the T, curve the finger. Let me try to do, it's hard for me doing this sketch, the right side. This is my finger. Okay, this is my hand, and the thumb pointing to the normal vector. So it's tangent. I touch the arrow for the tangent. I try to rotate my finger to touch the arrow for the K, and give me the thumb, the normal vector. Okay, entonces the tangent vector is in 3D, because remember cross product is 3D. Unfortunately, the tangent vector or the dr vector is called the ds vector. I copy here. Look, is dx, dy, and 0, because I consider it the third dimension. And k, you know, is 0, 0, 1. So we have unit vector and the c component, no? And the dot product, this quantity, this product is ijk. This is dx, dy, and 0. And the answer here is 0, 0, 1. And when you perform this, okay, I'm boring to do that. We get the vector, and the vector is dy, comma, minus dx, comma, 0. Therefore, when you set up the flux integral, that way, look, suppose que the vector field is PQ en 2D, ¿no? Y the dr o mds, que es this, is dy, minus dx, 0, pero okay, I omit the third dimension. I do not omit the third dimension in the cross product, because it's mandatory. Cross product is defined in 3D. However, in 2D, I come back and I remove the C component. So it's basically the line integral is dot product now, dot product is P dy minus Q dx. And this is the formula of compute the flux integral. So this is equivalent to this. Okay, compare. Circulation, flux. Circulation is line integral, vector field, dot product tangent, ds is equal integral p dx plus q dy. Circulation. Flux integral, C, vector field, That normal vector is a vector, vector, vector. ds es no vector, ds es scalar. Es integral p dy, wow, change, minus q dx. It's a flux. And remember the interpretation for the flux. I repeat again. Si you suppose que the vector field represents the velocity of water, is the amount of water passing through this surface. Que maybe this surface is, I don't know, si es closed o es no closed, es bounded. O sea, es only one. Let me try to do one example of the flux. And we are doing exactly to understand the meaning of this, the classical example. Suppose I come back to this example that I like so much, que is this example number 5, no? Example 5 today. Suppose the vector field is x comma y, the radial, and I compute the integral, the vector integral flux in the classical curve, que is the unit circle. 1. Remember, our vector field is radial, it's totally like that. Now, the integral that I want to compute, que es the flux, is the integral of the f double m ds. And the curve C, que is this curve. In this curve, I am boring to do the parametrization. It's cosine t, sine t, t vary from 0 to pi. And dx is minus sine t dt, and dy is cosine t dt. Okay. I repeat again for 2 reasons. Reason number 1, I very well know the behavior of the vector field. See, I put another, this is weird, I don't understand very well. However, the thing I want to differentiate is the circulation meaning and the flux meaning, right? And why not? I compute this using the new formula, no? Que es integral in p dy minus q dx. And this integral is from 0 to pi when you are doing the parametrization. In this case, t parametrization, because this circle is countable using cosine sine. No? And p, who is p? This is p, and this is q. Entonces p es x. ¿Y who is x? Cosine. Cosine t. dy. Who is dy? And dy is also cosine. This is cosine squared dt. Plus no, minus. Minus. Look at the formula. Who is q? Well, q is y. Who is y? Is sine t. Multiplication by dx. Who is dx? Is negative sine t dt. So we have another sign, and we have another negative, become positive. This is a square dt. Happens similar situation, no? In this case, the sine square cosine plus cosine square 1, and integral dt is t, and then say 2 pi. But the flux is not 0. It doesn't matter, no? It's conservative vector field, because it's different idea. In this case, the vector, the normal vector is in this direction. And the normal vector is in the same direction of the vector field. Therefore, the flux is positive. Because some water, I suppose that inside here we have a source of water, a house. Not necessarily water, guys, it's electric field, maybe, electric charge. Okay? Let me try to show you one algebra script que illustrate very well this idea. Let me try. I don't know if here or not. See, yes, there you go. Pero no this one. Open Flux. Okay, save. Okay. Boom, it's going. Okay. Let me share the screen. I try switching. Boom. Wow, what the hell? Okay, the vector field was the classical vector field, que es radial xy. Okay, and look at that. And the tangent, the normal vector you put in red color, look at that, a flash here. Is in the same direction for the vector field. Therefore, the flux integral is not zero. It doesn't matter que es conservative or not. Conservative is valid for the circulation. Si es flux integral, no. Okay? Let me try. And what do you think? What do you think can happen if you, do you understand or no? Sure? You see? The same mathematical conclusion. Okay, physically. Now, Giraldo, look at that. I want to change the vector field. Like a hurricane. This is minus y and x. Bam. Hurricane. Entonces, in this case, the normal vector, do you see que es the red one, is perpendicular always to the vector field. Therefore, the flux is zero. So the hurricane, you know, rotate and border the curve. O sea, no water or no air passing through the surface because it's perpendicular. Okay, let me prove mathematically this idea. It's the same, or similar. Do you see or no? Physically, now let's go mathematics. Example 6, switch it to the whiteboard. Boom, whiteboard. Boom, whiteboard. Example 6. In example 6, I want to compute the circulation, no, coño, flux integral, but in different vector field. The vector field is the hurricane vector field, que es minus y, x. I don't want to do the parameterization again because it's exactly the same. The parameterization depends on the curve, not the vector field. Now we're using the famous formula. This famous formula. And the integral from 0 to pi, in this case, this is P, this is Q. Be careful, que my vector field change. So P is minus y, and minus y is sine. Y is sine. This is minus sine. Minus sine T. A P. dy is cosine. Look at that. dy is cosine. Cosine T dt. Minus Q. Pero Q is x. And x is cosine. Cosine T multiplication by dx. And dx is minus sine T dt. Well, we have double sign here, become positive. So actually, that part is cosine T, sine T dt. And this is negative, cancel out. The answer is 0 flux. Wow, amazing. I like that. Do you understand this or no? Okay, guys, the most important for me now is, because I promised that we continue working with the line integral. Line integral is one way to visualize global property of the vector field. So in the last class, we see local in the one specific point. Now we have no specific point, we have a curve. or region, depending if it's closed curve or not. And we have the classical scalar line integral, que normally some book or some people call line integral different type ds. Entonces, time ds es scalar, because the function is x, y ds, scalar, line integral, or type ds. Everyone understands this. However, we have vectorial, and vectorial is dr. And dr, remember, is a tangent vector double ds. Okay, ds is, this ds is exactly the same as this. This is scalar. So this is infinitesimal r length. Entonces we compute circulation. And this belong to the category of the non-scalar. This is a scalar line integral. This is a vector line integral. And we have two kinds, circulation, and when you have m that ds is flux. Okay? Okay, do you understand this or no? Okay, and the rest of the night, get 5 minutes. Okay, super. We are the best. I want to introduce new chapter. Okay, we discussed it Monday in detail. Okay, it's about the fundamental theorem of calculus. You know that, right? Pero for line integral. Wow, new thing. Okay. I want to recall the classical fundamental theorem of calculus. It's integral from a to b of the derivative of the function is equal to the antiderivative que is f, evaluating between b and a. You remember that very well, no? Calculus 2, calculus 1. However, we have new one, que is fundamental theorem of calculus of the line integral. Entonces, I know, see this line integral, the integrand function is the gradient of the one potential function. I know very well that dr is circulation, no flux. I know okay, this vector field, this is a vector field, for sure. This vector field is conservative because come from for the gradient for the one potential function. Therefore, the potential function exists. Therefore, ese vector field is conservative. Okay, entonces now I know when this situation happens, the circulation and the one closed trajectory is 0, but this is path independent. So it doesn't matter. Okay, let me try to explain this idea in graphically. So when this situation happens, this vector field, okay, this vector field, que I suppose que se come from for the gradient circulation and the closed trajectory. O sea, what is the symbolic way to indicate closed? Look at that. Closed trajectory. This is a new notation. It's nice. Es 0. Because this vector field is conservative because come from for the gradient of the one hypothetical potential function. And this is path independent. That means that when you integration for the one curve is equal to the integral for another curve. Because the most important for us is the endpoint. Okay, you have 2 points, P1, P2. P1, P2. You travel for this. The work done is exactly the same as you travel for this. Because the important is the point, is the potential point, the start point and the end point. Therefore, the fundamental theorem of calculus say, wow, she is conservative because come from for the vector field. Well, the only thing you should do is evaluate the function, the potential function, and the start point, and the end point, sorry, minus start point. Okay, and this look like similar to this. Yes or no? Let me see the correspondence for this. This is a line integral. This is the ordinary integral. This is the derivative. This is gradient, que is more general than derivative in multi-dimension, maybe 2-dimension or 3-dimension. And you find one potential function, que is the antiderivative, but it's the anti-gradient. Remember, anti-gradient, que is backward, and you evaluate the point, last point, final point, start point. Okay, there's a potential function is possible to find the computed word. So you say, don't need to compute the word done using the integral. No. See, you will be able to prove que our vector field is conservative. Entonces, I go directly to find the potential function and evaluate in between the endpoint and the start point. And how do you know que es conservative? Because the curve is 0. Because the curve of the vector field is equal to 0. Okay, so this is the idea. In the next class, we have a vector field. We determine if it's conservative or no. After, yes, it's conservative. Super, good. I am happy. Now you determine the potential function. And you evaluate in the endpoint minus the start point. Exactly the same. This is the fundamental theorem of calculus of the line integral. This is another possibility. One door is open to compute the line integral. So how we compute the line integral? Well, we studied today parameterization. Okay. Parameterization is you can parameterize using t or using x. The conventional t or the ordinary, we call it another way, x parameterization. It's easier. And we're using the formula p dx q dy, depending si es circulation or es flux. Okay, and this theorem opens the new door. In the particular case, when the vector field is conservative, you find the potential function. The potential function is the anti-gradient, and the calculus 1 is called antiderivative, and calculus 3 now is anti-gradient, and evaluate the function and the end and start. Super. Next time we discussing problem about. I promise that we have another way more to compute the line integral. The line integral is important, extremely important. Any question? Any question? Super. Brandon, Heidi, Leonardo, David, Jocelyn, Omar, all good. Fiddy, Ricardo. Okay, guys. Sorry because I forgot to record one big part of the lecture.